double alkenes. That's all it means. We could also extend this to trienes, 3 alkenes, etc. And there's 3 types, actually. Okay. And there's 3 types. They're quite distinct from one another, and we're going to talk about these 3 types right now. Well, my camera will focus eventually, I promise. I think it just needs a little more text to look at. The first type of dienes are called non-conjugated. Non-conjugated. And the best way for us to describe non-conjugated dienes, I think, is to draw one, and then we can contrast it to a conjugated diene. We'll see the differences right away. Okay, non-conjugated diene. I'm going to draw an alkene. I'm going to draw an sp3 hybridized carbon, bridging it, and then I'm going to have it attached to another alkene. Okay, so this is an example of a non-conjugated diene, and the key feature is right in the middle here. We have at least one sp3 carbon. We could have 2, 3, 4, 5, 6, 7, 8, 9, 10 sp3 carbons, or any sort of variety of things. But as long as we have one sp3 carbon in between the 2 pi bond systems, we have what's called a non-conjugated diene. And the key thing about non-conjugated dienes is that this alkene and this alkene, that reactivity is independent of one another. Let's say that reactivity is independent of each other. That these 2 alkenes react in all the exact same ways that a regular alkene would react. Okay, so reactivity is independent of each other. These things just react as independent alkenes. Maybe that's another way to state this in your notes if you wanted to. That reactivity is exactly the same as 2 alkenes. The more important one for us is going to be called conjugated. And these are thus conjugated dienes. You already know what one conjugated diene is because you read about it. It's the most important diene of our discussion today. And it's where we have 2 pi bonds really quite close to one another. And a better way to look at it is that we have sp2, 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 sp2 hybridized carbon all in a row. We have a continuous system of sp2 hybridized carbon atoms. Okay? If we look above, we had sp2, sp2, and then there was a break in the sp2 system. We went to sp3. We could have more sp3s here, but then we ultimately have another alkene somewhere else in the molecule. For conjugated, they're all together. Maybe we can just draw a few extra examples today. Usually I don't do this, but let's take a bicyclic system, just 2 cyclohexane rings, and we're going to make a diene. This particular diene is non-conjugated. Next to it, down here, let's make a conjugated one. This would be a conjugated diene and a non-conjugated diene. Here we have sp2, all 4 in a row. Okay? Up above, we definitely have sp3s hiding in between the 2 alkenes. And so this is a diene because it has 2 alkenes, but they're not continuous, so it becomes what's called non-conjugated. And if they're continuous, all in a row, it means they're conjugated. And again, this is the type of system we're going to be putting all our attention on in today's lecture. There's something special about alkenes when they're in this particular 1, 2, 3, 4 sp2 atoms in a row. They're not particularly special when there's an sp3 atom in between here, and instead these behave just like regular alkenes would from our previous lectures. The third type of dienes are very, very special. You won't study them unless you go on to study chemistry at a graduate level, but we're going to just describe them. They're called cumulative, and there's another name for these, and they're called allenes. We won't do anything with them But this is an example of an alene. I guess we can put all H's here. It's definitely a diene. There's alkene and alkene. And you might say to yourself, well, this looks almost the same as conjugated. These look quite similar to one another. The main difference here is what's the hybridization at this particular carbon right here. Someone can just write it into the comments for us, for everyone to see, or just to me. SP. Thanks, Jennifer. You're awfully snappy today. This is SP hybridized at this particular position. SP2, SP, SP2. So this is definitely different than conjugated. It has very different reactivity. It's very special, and we won't study it this particular semester. And as undergrads, you definitely won't see this type of compound again, I don't think. Okay, unless it's a very specialized case. The one that's very special for us is conjugated. It's going to allow us to expand upon what we learned with alkenes very readily and learn a few new things. We're going to talk a little bit about the anatomy of these things, of conjugated dienes right away. First, we're going to draw butane, and then we're going to draw butene, and then we'll draw 2-butyne. So we have butane, 2-butene, 2-butyne. And the central carbon-carbon bond distance 1.53 angstroms. These are not numbers you need to memorize. A very short unit of length. And for an alkane, carbon-carbon bond is about 1.53 angstroms. And we know that double bonds are stronger than alkenes. They're also shorter. The two carbons, this is the distance we're measuring. The two carbons are actually getting closer and closer to one another. The distance is shorter. The bond is stronger. We know that a double bond isn't twice as strong as a single bond, but we know it's about 50%, 60% stronger. When we get to an alkyne, then, we know it's not 3 times as strong as a single bond. It's about 2 or 2.5 times stronger. And we would then anticipate that it's even shorter, too, right? All these additional bonds bring the atoms closer and closer together. Right here, we're going to draw a diene. Draw it right here on purpose. This central bond on paper looks like a single bond. It looks like we have double, single, double. It turns out there's ways to measure this particular bond distance, and it's a little bit shorter than a single bond and a little bit longer than a double bond. Right? But it's still a single bond, so why is it so short? And there's 2 possibilities for why this is this way. One thing we're going to say about this particular bond is that it's not a true single bond. Meaning it doesn't behave like a real single bond. If it did, it should be a little bit longer. And part of the reasons why this becomes a little bit shorter has to do with conjugation and resonance. This particular bond is getting a little bit shorter, a little bit contracted, because these pi bonds actually are sp2, 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 sp2. There's 2 pi bonds connected in very close proximity to one another. There's no sp3 bonds between them, and it contracts a little bit. And these 2 pi bonds we're going to see are going to communicate with one another. Okay. So these 2 pi bonds are going to communicate with one another. It's going to be a little bit different than what we might expect if we just said, oh, well, this is just a plain single bond hiding in the middle here. Let's actually do a reaction, and you saw some of these reactions already in your study. Just going to fix the camera here.